Imagine walking beneath a ship that, just days earlier, was crossing the ocean. Above your head, there is no building, no bridge. There is a steel hull weighing tens of thousands of tons, propellers larger than cars, and a structure almost no one ever sees while the vessel is afloat. And that raises a question that seems impossible. How do they pull a giant ship out of the water to repair everything hidden underneath? Today, you will discover how these monsters of the sea stop floating and reveal their secrets. Here on Invisible Structures. The first image many people picture is a colossal crane lifting the entire ship like ordinary harbor cargo. But that idea quickly falls apart. Large vessels were never designed to hang from cables. Their weight is immense, their structure is long, and poorly distributed support could bend steel plates, strain internal sections, and turn routine maintenance into a disaster. The secret lies in controlling the water. There are two main approaches. In a fixed dry dock, the ship floats into what looks like a giant swimming pool. The entrance is then sealed, and the water is slowly pumped out until the hull settles onto supports below. With this method, the ship barely rises at all. The world around it is what descends. In a floating dry dock, the logic changes. A massive platform deliberately sinks, receives the ship between its sidewalls, and then rises again, lifting the vessel clear of the water. It sounds simple when explained quickly, but every inch of alignment matters. And why go through all this trouble? Because critical components spend years hidden beneath the sea. That is where corrosion develops, hull damage appears, barnacles gather, propellers fail, rudders wear down, and valves and water intakes malfunction. While the ship is afloat, some repairs require complete, dry, and safe access. That is the real challenge. Removing a giant from the water means letting the vessel settle without deforming its own body. A misplaced support can concentrate tons of pressure where the hull was never designed to bear it. Before we continue, subscribe to Invisible Structures, because the next question is even more remarkable. How can an entire ship land on a row of blocks hidden beneath the water? For a giant ship to settle onto blocks hidden underwater, the operation begins before it even reaches the dock. Engineers study the shape of the hull, its internal reinforcements, and the points that can carry weight without deforming the structure. It may sound excessive, but this preparation determines whether docking is safe or thousands of tons press against the wrong place. At sea, water supports the hull across its entire submerged surface. It is like an invisible hand pushing the vessel upward at millions of points at once. Inside a dry dock, that hand is about to disappear, so the ship must find a new source of support, calculated with absolute precision. At the bottom of the chamber, keel blocks are aligned along the center, exactly where the strongest part of the ship must rest. Side supports help keep the vessel stable once it stops floating. Compared with the ship, these blocks look impossibly small, but they transfer the load into the reinforced floor of the dock, like the legs of a gigantic table. The dock remains full and open as the ship floats inside, guided by tugboats, cables, and winches. The maneuver is slow because the vessel must be positioned over a row of supports concealed by the water. The crew is not simply parking a ship. They are aligning an enormous hull with invisible points on the floor. Once the position is confirmed, the gate closes. The ship is now inside an industrial pool separated from the harbor. The pumps begin draining the chamber. At first, almost nothing appears to change. The hull continues to float, held up by buoyancy, while the water level slowly falls. Then comes the critical moment. The keel touches the first blocks. That contact cannot be sudden. The ship's weight gradually shifts from the water to the supports, and every inch of descent must confirm the calculations made before the operation. Teams monitor the vessel's angle, alignment, and load distribution. If anything looks wrong, the process can be stopped, because a mistake here does more than scratch paint. It can strain plates, tanks, and internal welds. As the water drops, the side supports are adjusted to keep the ship from leaning. They do not lift the vessel. They hold it steady while the hull loses the support of the sea and begins resting on the floor of the dock. When the water finally disappears, the impossible becomes real. The propeller emerges. The rudder appears. The underside of the hull, once hidden beyond sight, becomes a work site. Technicians can walk beneath it, build scaffolding, inspect valves, and search for damage that would remain invisible while the ship was afloat. That is the secret of a fixed dry dock. No one lifts the ship like suspended cargo. The vessel remains almost exactly where it was. The sea is simply removed from beneath it. But what happens when a port has no excavated chamber, reinforced walls, or watertight gate? How can a ship be removed from the water without that kind of permanent structure? If a fixed dry dock resembles a pool losing its water, a floating dry dock is almost the opposite. An entire structure deliberately sinks to lift a ship out of the sea. From a distance, it may look unfinished. There is no gate sealing an excavated chamber and no concrete walls anchored to the ground. Instead, there is a massive platform, usually open at both ends, with tall sidewalls and a base that acts like a giant hull. Inside that base are ballast tanks, and they are what make the magic possible. When the operation begins, those tanks fill with water. The dock grows heavier and sinks in a controlled descent. Its central platform drops below the surface, while part of the sidewalls remains visible, like enormous rails marking the ship's path. The vessel then floats between those walls. Cables, winches, and tugboats make slow adjustments because the hull must be positioned above the submerged platform. But now there is one important difference. In a fixed dock, the floor does not move. Here, the base that will support the ship is floating too. Once alignment is complete, the process reverses. Pumps force water out of the ballast tanks. The dock becomes lighter and rises. First, the blocks installed on the platform touch the keel. Then, as the dock continues upward, the ship's weight transfers onto the structure. It is as if a steel island were emerging with a giant on its back. But that ascent cannot happen carelessly. If one side rises faster than the other, the entire structure may tilt. If the bow gains support before the stern, or one section takes too much weight, the load can concentrate where it should not. That is why the tanks are emptied in a controlled sequence, while operators monitor level, angle, and load. This is the most remarkable part of a floating dry dock. It does not overcome the ship's weight through brute force. It uses the same principle that keeps the vessel afloat: buoyancy. By controlling the water inside its tanks, the structure decides when to sink, when to rise, and how to carry something that cables could never lift. The great advantage of this system is flexibility. A floating dry dock can expand a shipyard's capacity without requiring a monumental excavated chamber. It can also be relocated and used in ports where building a fixed dock would cost too much. That is why these docks appear in commercial, military, and offshore support operations. Both methods solve the same problem in different ways. In a fixed dry dock, the ship remains in place while the water falls. In a floating dry dock, the dock itself sinks, receives the ship, and then rises again with the vessel on board. After overcoming all that engineering, an even more intriguing question emerges. What do workers find on the part of the ship that spent months or even years hidden beneath the sea? Tell us below, which is more impressive, the fixed dry dock that makes the sea disappear, or the floating dock that sinks to lift a ship? And tell us where you are watching from, because it is always fascinating to see where the explorers of invisible structures come from. When the hull finally emerges, the first reaction is almost always the same: surprise. The surface that looked smooth and invisible while the ship was afloat now reveals scars, marine growth, rust, scrapes, and evidence of a silent battle against the sea. The work begins with an inspection. Technicians circle the vessel, searching for dents, cracks, deformation, corrosion, and impact marks. Some may look minor, but they can reveal that the ship struck something underwater or lost thickness in a critical area. The steel is measured to determine whether each plate is still strong enough to return to the ocean. Next comes one of the most visible enemies: marine growth. Algae, barnacles, shellfish, and layers of slime cling to the hull, as if glued in place. This is more than dirt. Every irregular surface increases drag through the water. More drag means harder working engines, greater fuel consumption, and lower efficiency. A heavily fouled hull can make a ship burn far more fuel to cover the same distance. That is why the cleaning is so intense. Ultra-high-pressure water jets blast away salt, slime, barnacles, and deteriorated paint. The sound is violent, the sight is striking, and the process looks like an old layer of skin being stripped away. Scrapers and mechanical equipment tackle the toughest areas. Only then does the true condition of the steel become visible. With the hull exposed, repairs begin. Corroded areas are marked. Damaged plates may be cut away and replaced with new steel. Welds and joints undergo careful inspection, because a small flaw on land can become a major problem at sea. If the ship suffered a collision, grounding, or impact, crews reshape deformed sections and reinforce damaged points. But the hull is not the only star of this hidden world. The propeller is examined for cracks, bending and cavitation damage, erosion caused by bubbles forming and collapsing violently as it spins. The shaft, seals, and bearings must also be in working order. The rudder's pivot points are inspected, along with side thrusters that help some vessels maneuver inside ports. Even anchors and chains may be included in the overhaul. The chains are stretched out, washed and examined link by link. Mud, rust, and debris are removed as deformation and wear are identified. It may seem like a small detail, but the chain is also essential for safety when an enormous mass must remain firmly anchored in one place. Finally comes protection. Sacrificial anodes are replaced at strategic points. These metal components are designed to corrode first, sparing more important parts of the hull. It is like offering the sea an easier target before it attacks the main structure. The surface then receives fresh protective coatings and paint. Anti-corrosion layers come first. Next, anti-fouling paint helps prevent barnacles and marine organisms from returning. Draft marks and other markings are restored, giving the hull both renewed protection and the visual references needed for operation. The dock now reveals its true purpose. It does more than remove a ship from the water. It transforms an inaccessible part of the vessel into a massive work site, where every crack, every valve, and every inch of steel can determine whether that giant is ready to return to sea. After so many repairs, one final question remains. How do they return the ship to the water without allowing a single mistake to ruin everything? Before the ship returns to sea, no one simply presses a button and releases it. The process begins with an almost obsessive inspection. Welds, plates, valves, water intakes, and coatings are checked again. Tools, cables, scaffolding, and equipment must be removed from the dock. Every opening that will be submerged must be closed, tested, and secure. The reason is simple. Once the water returns, it does not forgive carelessness. In a fixed dry dock, the entry process runs in reverse. Water slowly flows back into the chamber. At first, the ship remains on the blocks. Then, as the level rises, buoyancy returns, and that invisible force once again takes the weight of the hull. This moment demands control. The crew checks that the ship rises evenly, that it is not leaning, and that no section remains pressed against the supports. Slowly, the giant leaves the floor of the dock and is carried by the sea again. Once everything is balanced, the gate opens and the vessel is guided outside. In a floating dry dock, the process also reverses. The ballast tanks fill with water, making the dock heavier and causing it to sink. The platform descends, the ship regains its own buoyancy, and the hull lifts free of the supports. Once there is enough depth, cables and tugboats guide the vessel out between the sidewalls. The dock then empties its tanks and rises back to its normal position. But leaving the dock does not mean immediately returning to normal service. Steering and propulsion systems are checked. The propeller, rudder, valves, and hull-related equipment undergo testing. In many cases, the ship performs sea trials to confirm propulsion performance, maneuvering response, and the operation of repaired systems. In the end, the opening paradox is resolved. A gigantic ship does not need to hang from cables to leave the water. In one method, the water disappears around it. In the other, an entire structure sinks and rises again. Everything depends on controlling weight, buoyancy, balance, and precision. A hull that crosses oceans may seem self-sufficient while sailing, but to keep facing the sea, it must occasionally reveal the part almost no one ever sees. To keep discovering the invisible structures that support the modern world, subscribe to Invisible Structures and tell us below, Which part of this process surprised you the most?